Hi everybody. Today I'm going to talk to you about a brief of some circuits for building shifting operations using combinational circuit instead of registers as we learned before in the 2300 course material. So there is something is called Barrell shifter, which is literally a network of multiplexers used for performing parallel input, parallel output, parallel input, parallel output shifting. So you don't need to associate this with registers with clock as a sequential element unless the critical path is very quite long. So then you can outperform pipeline. So in the beginning, just to remind you, what is shifting and rotation? So there is one thing is called logical shifting. There is another one is called arithmetic shifting. And there is another thing is called rotation. So since it's a register is performing, so you can those guys category can be in the left or the right side. Just a few examples, then I can move into the left side. So for the example of the shifting, so imagine that somebody's telling you I'm using logical, so that means you don't care about the most significant bit. So imagine that my register is a 4-bit. So here is basically R1, R2, R3, R4, and those are the name of the bits in the register, which is a 4-bit. If somebody's telling you perform shift logical, right, one time, so basically you are pushing from the left toward the right with zeros. So in that case, the output of this is equivalent to 0, and that R1 will be here, R2 will be here, and R3 will be here, and R4 will be completely out, which is spelled out and is not stored. So this is the content of the registers. If you perform another shift toward the right, you're going to push more 0, then R3 will be out, and so on. While a rotation, it can be rotate left or rotate right. Let's perform an example of rotate left and rotate right. So if you already have here a register for bit B0, B1, B2, and B3. If you would like to perform here rotate right, so rotate right 1. So that means I'm pushing from the left to the right with what? With the discard bit from the right. It doesn't mean, what does it mean? It means that this bit will be pushing to the other circle or ring form. So what is the output of rotation right in this case? It's gonna be, here is the register 1, 2, 3, 4. They're gonna be B0, B3, B2, B1. So you shuffle in a ring form towards the right. So if you would like to perform rotate left 1, in that case, I'm gonna take it as 1, 2, 3, and this is for the original value here. So I'm pushing toward the left from the right. So that means the B3 will be the one I push with. So in that case, it's gonna be B3, B0, B1, B2. Hopefully it's clear. It is very important for the processing data. It's very important in the computations. But as you can see, doing this process is belong in a time. So if I say rotate left to right or left, normally they use something is called shift registers configuration. Shift register configuration. And normally the configuration is the following. Whether that, the input and output relationship will be SISO, which is the serial input, serial output. That means I'm gonna feed the register in a serial way like this. Or there is PISO, which is basically parallel input, serial output. Serial output. or which is look like that. I'm just refreshing your knowledge input, and your output will be like take it like this one shot. And there is serial input, parallel output, which is basically no, basically I perform here the wrong ones. It's actually SIP. Oh, I'm sorry. Now I'm actually doing what? PISO, which is basically parallel input, serial output. So parallel input like this. And you're gonna get the output from here. Here's the input. Or you can have PIPO, which is the parallel in, parallel out. So that means I have a 4-bit at a time, so I'm gonna push this at the same time and I get the output at the same time. That's actually a serial input, parallel input, parallel. So Princeton University team came and say, if you're gonna perform such a kind of thing, why you waste your time and use a sequential circuit? Why you don't use a combinational circuit? And in this case, this combinational circuit would be what? Registers. Sorry, multiplexers. So the elements gonna be heavily used in a barrel shifter is a 2x1 multiplexer. So you already have I0, I1, and you already have your select, and you already have here the output, which is P. If select equals 0, then P is equal I0. If select is equal 1, then P is equal I1. Combinational circuit, straightforward. If you remember, what does multiplexer look like? Is an and here is negated of the select with the I0, while select is going like this, and you already have I1, and there is an OR gate for the gathering the information. And this is the circuit, is basically a multiplexer. So far, so good. Now, let's build a barrel shifter. So in a barrel shifter, let's perform an example of 4-bit, which is basically what we need for this lab. So I would like to build a 4-bit barrel shifter. So let's see how this barrel shifter will be working, right? So regulation says it's a 4-bit, so that means I need a 2x multiplexers per every single level. How many level I'm gonna have? It's gonna be log 2 of number of bits I have. So it's gonna be 2 levels. Let's see what this incites me. So if it's a 4-bit, so that means, as I said, it's gonna be 4 multiplexers in a level. But then, I said how many level? 2. So that means I have another level with multiplexer like this. How it gonna work? If you remember in a binary, we have 2 power 0, 2 power 1, 2 power 2, boom, 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 2 power n. Do you agree? In that particular case, what you can do, you can also do edit distance between of them. What does it mean? So imagine that my input is I0, I1, I2, I3, and this is my input. And my output is basically P0, P1, P2, P3, right? So here is my final output. Here is P0, P1, P2, P3. Do you agree? Now, let's see how I'm gonna distribute the input. So since there are 2 levels, so each level will be representing the power of the 2 because it's a binary system. So here, let's call this S1, and this representing 2 power 0. So what is 2 power 0? 1. So that means the distances between the neighbors' bits will be 1. So if I select here I0, so the neighbor is I1. And this is when it's 0 and it's 1. And let's call this V0. I'm done? No. Every single multiplexer representing the bit in a position. So in that case here, it's gonna be I1. Then the distance will be what? 1. So it's gonna be I2. And it's called V0. Then you already have here what? I2. And the distance is gonna be I3. and then let's call this V2. Then, this is gonna be I3, but I3 plus 1 is what? I4. Is there any I4? No. What we're gonna do, we're gonna make modulo of 4 because it's a 4-bit. So which is gonna turn what? 4 modulo 4 is what? 0. So that's gonna be what? I0. And let's call this E3. Are we done? No, we're not done. So in that case, we're gonna go into the next level, how we're gonna connect it to the output level. So here it's gonna be S0. So be sure that this select is for all of the register, all of the multiplexers in the level. So that means this is S1, this is S1, this is S1, and this is S1. Same thing. Here it's gonna be S0, here is S0, here is S0, here is S0. Now the neighbor, the second neighbor is 2 power 1. What is 2 power 1? 2, right? So still, now I'm gonna start with V0. So V0, add 2 to it, so it's gonna be V2. Second position after V0 is what? V1. So gonna be V1. Add to it, so gonna be what? V3. Then the position after is V2. Add to it 2, so gonna be V4, but we don't have 4 because it's a model of 4. So that meaning gonna be what? V0. Then here is V3. You're gonna add 2 to it, so gonna be V5. V5 modulo 4 is basically what? V1. So now we already made the network of the barrel shifter for the for that. Let's see whether this thing is working or not, right? So if you make a truth table like that, and then you can call here S1, S0, and then you have here 4 possibilities. 1, 2, 3, 4 possibilities of this type of register configurations, right? So 0, 1, 0, 1, 0, 0, 1, 1, and here I have the position of the output, which is basically 4 location: B3, B2, B1, B0, right? Let's see what the values will be expected out of this when the configuration of S0 and S1 change. So if you look very carefully, you will find that when it's 0, that means my V0 is equal I0, my V1 is equal I1, because S1 is equal 0, right? And here is equal what? I2 is equal I3. So far so good. Now since S0 is also 0, so that means this V0 will go here, right? And the value of V0 it was I0, so this I0. They're gonna be V1, and V1 here is I1. They're going to be V2. V2 is basically I2. And they're going to be V3, and V3 is I3. So we're going to write it down here to be what? I3, I2, I1, I0. Which is basically the original of the message. If the message is sorted like that, it's going to be coming out of that if the S0 and S1 is equal to 0, 0. Are we done? No. Now, we're gonna clear this spot and jump into the second configuration. And then the second configuration, S1 is still 0, so this is still the same, right? While S0 is 1. So that means B0 is equal V2. It's equal V2. B1 is equal V3. B2 is equal V0. B3 is V1, right? Now we are taking the values of them. So V2 is equal what? V2 is still I2. V3 is what? I3. V0 is what? Is IC. V1 is what? Is I1. So let's sort it. It's going to be here no, I'm going to be here I0. I'm sorry. Sorry, I flipped it. So if you look very carefully to it, so basically, S0 is 0, is 0, is 0. So still gonna be V0, I'm sorry. V0, V1, V2, V3. While you know the S1 here is gonna be 1. So 1 is gonna be here I1, I2, I3, I0. So in that case, it's gonna be what? It's gonna be I0, I3, I2, I1. And then you will move forward to be I1, I0, I3, I2. They're gonna be add two more to be I2, I1, I0, I3. And if you notice, this is basically a rotation period. So now we understand the barrel shifter. So what is exactly needed from you as an assignment? So if you remember carefully, the up-down counter, it was an 8-digit performing, right? It was 8-digit what performing. So you already have here BCD, BCD, BCD up to 8, right? And they connected to each other as we have done before. The output of this is a 4-bit, right? Here also 4-bit. Here is also 4-bit. Here is also 4-bit, and so on. And those were hooked into the digit, right? What I need from you, it's a really easy lab, by the way. It takes for you maybe 15 minutes, is to put here barrel shifter. And then the output of the barrel shifter will be going into the digit, to the digit 1. They're gonna go into digit 2. They're gonna go into digit 8. So possible? Are we done? We're not done. Why? Because now you're going up down, right? And I don't have loading, it's just up down counter, that's it, right? But this barrel shifter, it has what is 0 S1. That one has is 0 S1. That also have is 0 S1, and so on, right? So, but we have 16 switches. You agree? So what about if I do the check, which is basically the first 2 switches will be responsible on this S0, S1. The second 2 switches, they're going to be responsible on changing the rotation of the barrel shifter for the second digit. And then the third for the third up to the 8th. Then you are using all of the 16 switches. Sounds good? Now, how I'm going to stop the, like enable and disable the up down counter. So you already have push button, right? Push button. You have a push button. That's gonna be the trick, all right? So I want you to like brainstorm and see how we're gonna do it, okay? So in the push button, when you push one time, you push and you release, right? You push and you release, right? So if you push and release one time, what will happen? That will make this 8 digits running. So let's write it down because I know guys you like instructions. 1, design 4-bit barrel shifter. 2, and 4-bit barrel shifter between the output of 4-bit BCD and the input bare digit. 3, right? Assign 2 switches bare digit to control the barrel shifter. before I'm out of switches, how I'm gonna enable and disable, and in the top of that, make it up or down. So that means, you know, you need to design a circuit, and this is for you to think about it because that's a system, okay, for you to think about it, which is doing the following. One push button will be dedicated for who? For the whether that is enable or disable the whole entire circuit, enable and disable the 8-digit up down counter, right? So you push, then release the button, but still enable will go high. What does it mean? You know, the circuit will be run. Then if you push and release again, the enable will go down and everything will be paused. Another button, push button, will be for the up or down. So if I push, then I release. If I push, then I release, what will happen? Then, you know, I will be up mode. Then I push again, then I release, that will go into the down mode. That will be involved for a nice state machine. So I am not going to give you the solution for this. You need to think about it. So this summary, what? So, you know, you're going to design the full pitch barrel shifter. I already described it to you how you're going to make it. Then you already have the up-down counter. Every single barrel shifter will go in the top of the PCD per digit and connected to the digit. Then that control for the barrel shifters will be connected to the dedicated switch on the panel. You have 16s, and those are 8 digits, so that means 16s is enough. 2, 2, 2, 2. Then, you know, the trick you will add, which is basically 2 push buttons, one made for the enable of the circuit to be running, while the other is going to be made for what? For the whether it's going to be up and down. How it works? You push release, then you are enabling. You do again push and release on the same button, then it will be disabled. You go here in the second one, you push, you release, then it will be up. You push, you release the same button, it will be down. It's really easy, but I'm not going to tell you the trick. Think about it, right? Make the report as usual, make everything as usual. And if you have any question, don't hesitate to contact me. I will be more than happy to assist you. It was my pleasure to record this video for helping you to work on the lab number 8. Have a great night and talk to you later. Thank you.